Alright, hello, welcome to the August 2014 Programmable Logic in Practice. So I'm going to be showing you how to use this super cool, or I think super cool, ZPUIno Arduino Papilio or ZAP IDE. So this is a way of using a soft-core processor, and it's a little different. So there's some soft-core processors like the Xilinx provided ones, but this one is it's open source. And more interestingly is that the development environment is actually pretty simple, which is really handy. A lot of the times you just want a soft-core processor for doing, some basic housekeeping or some other work, or you just have a small FPGA. So this is really aims to make it a lot easier to get started. You don't need the entire software development kit or a whole bunch of other stuff. So it's actually really handy, not just for sort of the hobbyist thing, but real projects where you don't want the the engineering overhead of setting up a whole soft-core processor. Anyway, so it's pretty easy. You download the zip file. I won't do it now. It's a few hundred megs, nothing too major, and it gives you this this folder. And all you do is you open zap.exe. So zap.exe is based on Arduino. If you haven't used Arduino, don't worry. One thing a lot of people don't realize, it's really just C code, or C++ or whatever. So it's just like any other embedded development. It wraps it around its own little environment and gives it weird file names, but it's still, you can just write code as if you've always known, loved C. And you can even, of course, just compile outside of this environment if you want, using command line tools. But this is handy because it's a nice way to get started. So physically, what I've got over here, let me pull the webcam over, is this is a Papilio Pro platform. So this is underneath a wing here. So there's the FPGA board, and this just slaps on top. So it's got some switches and some LEDs that we can play with a bit. So it's an LX9 based board. You can, of course, use this on other LX9 or the Spartan 6s easily, or even other Xilinx FPGA parts. There's some examples using the XCS300 or something like that. Anyway, I just plug it in. There we go. USB cable's on, and it shows up in as a serial port. So where's our serial ports? No, so there we go. We got these two extra COM ports. So in the ZAP IDE, all you have to do is select the appropriate COM port. So of the two COM ports, I select the second one. The first one is, I think, used for JTAG or something for the FPGA. So we want the second channel. As a note, one thing you might have happen is that when you go to this tools menu, it takes a while to pop up. Why this is, if you have a Bluetooth radio on your chip, let me just enable my Bluetooth radio here. Because that can appear as a COM port, it really slows down the menu loading sometimes. So when I go tools, you see that menu does not come up. There it just comes up, and there's the serial ports listed. So it's really annoying, and all you have to do is disable it in Device Manager. Is the easiest way anyway, assuming you don't need Bluetooth for your mouse or something. Anyway, there we go. So now you can see the menu pops up right away. So I select the serial port. And the first thing we're going to do is we're going to select the board type. So the board type, what this actually means is you're telling it what FPGA physically board you're using and what bit stream you want programmed in. So I have a Papilio Pro LX9, and there's some other crap here. And this just means there's a bit stream that's configured with all this stuff. So the Logic Start Mega Wing, which is that board I have on top, so it's configured to use some of those peripherals. So we just go ahead and select that. And finally, we have to hit Burn Bootloader. Burn Bootloader, what it's really doing is burning the FPGA bit stream in. And the FPGA bit stream includes, as well as the code that sort of will bootload our own code, so we can upload data over the serial port. So the whole system's very slick because it it just has a attached flash chip, and it uses that for both storing the FPGA, so we confirm that that all worked. Yep, verified. So it uses that for storing the FPGA code and the source code for our soft-core processor. So we don't, it's really like a regular system. It just comes up and it's live. You don't have to deal with any stuff yourself. So let's do a simple example. Let's start with just making an LED blink. That's always a nice, so this is the blink example that comes with Arduino. These examples, of course, are not designed for the hardware we're using, so we have to change them a bit. So let's just save it somewhere. Test blink video. Hopefully I remember to delete this. So pin 13 is on the Arduino. That's not connected to an LED on this board. So I know, and there's a header file with all these in them. I'll show you later. LED 1, I think, is pin 40, or what's called pin 40. So we can hit verify, and verify is, of course, just compiling it. So there you go, it compiled it. And the upload button here programs it into the flash chip on the board. As a note, if you have a larger file, this was only a kilobyte, so there's nothing to it. You can hold down, if I hold down the control button, or what is it? Why isn't this working? But there's a way that it'll only upload it, rather than programming into the chip, it just uploads it to RAM, which is quite a bit faster because it doesn't have to reprogram the flash chip. So we can see if I'm holding the control button, it should say upload to memory, but it doesn't here. We can see the upload time is now just 0.17 seconds instead of 0.75. So that wasn't a big change, but it does, again, when I'm holding down the control key, it uploads it to RAM. So if you're doing development, that's a lot faster. All right, so let's look at what's happening in real life here. And if you can see, LED 0 is blinking. So that's it. We've just programmed a soft core processor into our system and then made a LED blink in, what's this, 7-8 minutes. So that's pretty good. It's nice that it's so easy to get started. But we probably want to do some more interesting stuff. In particular, we want to modify that soft core processor. So the first thing we're going to do is, well, we're going to look at the soft core source. Move all these windows out of the way. Get rid of that. So here's that ZAP IDE, and it's somewhere. We've got to remember now where it is. Examples. Oh, here we are. Papilio schematic library. I think you can actually access this from the ZAP IDE. So it has some tools here. Papilio. So you can just, I don't know which of these it is. But so there we go. That opened the directory that had them all, so you don't have to go through and find them. And if we go to the specific examples, so Mega Wing Logic Start. Oops. So what's this? So this one, by the way, when I had said, where do all the pins come from, this is showing you some of those pins. All right. So here's that Mega Wing Logic Start associated FPGA project. So this is what we're interested in, and you can see there's the LX9 version, and then this is a Spartan 3 500K or whatever version. So we're interested in this LX9 version, and I'll just open it in. I assume you already have Xilinx Project Navigator. Xilinx ISE, sorry, and you start Project Navigator open. Here we go. So let's say open project. Let's point it. So we want this PSL, Papilio Pro, LX9 project. And it takes a second to open. So there we go. So before we do anything else, well, we can look at the schematic. So this might be a little small on your screen, but hopefully you can see. And we have, so there's the Papilio Pro processor, and we've got a bunch of stuff connected to it, some various slots. GPIO pins and whatnot. So pretty cool. So what we're gonna do is we want to do a few things. First, I'm gonna recreate the existing project, so just to make sure things are working. Go back to my design and say generate programming file. So while that's going, what we also need to do is tell the Papilio or the ZAP IDE where let's go back to here, where that bitstream is located, because now we want to be able to program that into the FPGA all from within the same location. So there's this hardware directory, Papilio, nope, not Papilio, sorry. ZPUIno, somewhere there's a boards.h. So you just sort of go through all the directories. Nope. Now. Okay, so there's boards.h. We don't want the AVR8 though, is the thing. We don't want libraries. Okay, so ZPUIno, ZPU, here's boards.txt, not .h, sorry. And what you can see is this is the list of those things that came up on screen. So we're just gonna go ahead and take, what's our version here? This is the one we were using. Logic start, and I'm just going to copy it to the top of the file. So I'm going to do a few things. I'm just going to rename the variable there, so I'll just pp at the end. And that will now show up in the system. Of course, what it's still doing is pointing to the wrong the bit file. So what I had figured out is relative to this board's, relative to the main file. So you can sort of find where these are located to figure out the path directory. I'm going to point it to the file we're going to create. So starting from the examples directory, Papilio schematic library, examples, megawing logic start LX9, Papilio pro.bit. So this is the, assuming this is the final file that gets generated, and we can just confirm that. So examples, Papilio schematic library, examples, megawing logic start LX9, Papilio pro.bit, and you can see the timestamp is for today. So this means that we'll now be able to program into the board a file that we created via the standard FPGA development platform. All right, so that's looking good. And just as an example, so it should show up here. You might need to restart. Make sure I save this. Oh, I didn't save it either. So there's two problems. And I'll just restart the IDE. And here we go. So the first one in the list, and you can move them down if you want it to all be together, but I just have it at the top here. We can now see it's going to be pointing to my bitstream. And if I go burn bootloader, just make sure it found it okay. it seems to be programming it. I can see the lights on the board going dim. Alright, so I'm going to go through sort of a quick example here in that I'm going to help recreate the example from my article. So on the Programmable Logic in Practice site, there is the FPGA code. And I'll take you through a bit more of an example. So the two things we're going to use is the VHD, so the VHDL source file, and the schematic source file. So I'll copy those somewhere. So I'll just copy them right into the MegaWing Logic Start directory. So one of them has the same name, of course. So I won't copy that yet. So we do have the VHDL file there. So this is sort of showing, so what if you had your own peripheral you wanted to add to the whole system? So I'm going to do the normal thing. I'm going to hit add source. Just chucks it into the project. You know, it's not associated with anything. So you can go through it, and there is a whole bunch of these examples. So if you look through the, these are some of the ones I'm using, but there's even more examples in the directories. And it basically shows you we just have a simple wishbone interface. I also have a clock, and I have this pulse width modulation out. So I have an 8-channel pulse width modulation system. And I've made a really simple pulse width modulator where I just copy and pasted it a bunch of times. And you can see how we're using the addressing within the wishbone bus to select with pulse width modulation block gets connected in. So it's pretty cool that it can be, you know, really simple to add in your own blocks. So one of the things you'll want to do is place this into, so remember again we have this schematic entry, and that was VHDL. So we want to place that into this system. So what we're going to have to do is you click on the VHDL source file, and there's this option create schematic symbol. So you just double click on that, and it'll automatically pull out the ports and create the symbol. So you'll have to fiddle with it a bit to get the to get it to look just like these blocks. So you can see, for example, when you look at them, they have the wishbone buses on top, and it's not even marked which is in and out. So you have to edit the symbol a bit, I do admit. But in the schematic editor, I select, you know, this is our local library, and I can drop that block down. And hey, there we go. So we can connect this into one of the wishbone slots, and it should work. But before we do that, we're going to have to get the rest of the design sorted out here. So part of this will be deciding, I'm going to remove stuff that I don't need and add in our new block properly, and I'm also going to modify how the symbol looks so that it works. So I'm not going to care about this VGA stuff, so I'm just going to delete it. And if I want to, you know, I have this slot here. If I'm not going to use the slot, which I won't in this case, we just put a somewhere there's an empty slot option. Let's see, wishbone maybe. Wishbone empty slot. There we go. So that just sort of, I don't know, stops you from getting errors, I assume, at least, and makes the schematic a little nicer. So what else do we have here? Slot 6 and 5. So 6 goes to the SPI, so that's for the ADC, which we do want. We're going to use in our design. So if you read the article, you see I'm measuring a ADC and then using that to light a bunch of LEDs. The DAC, I think we can just leave. I don't actually use it in this case. And the other thing I'm going to do is, so these LEDs, what you can see is this logic start is basically using these GPIO. So there's this GPIO bus out. If you saw with the example when I said, pin 40 is set to whatever, that's connecting that to one of these LEDs. So we actually want to use these as with our pulse width modulation block. So I'm going to remove them from here. Oops. There we go. And just leave those unconnected. And the other thing we will want to do is edit the symbol. So, again, this looks, if you're making this, trying to make this look nice, it would be nice if this just could drop in, like, see how they all have the wishbone slots in the top. So we want to edit that symbol. So I think you can just hit edit symbol, and then you can move these around as needed. So the default view, when you look at the other ones, I'm going to put this below. It goes wishbone out first and then wishbone in. So we're just gonna, and we don't have all of the, everything's sort of just graphical in this thing. All that really matters, so these blocks here are where the actual connections are formed. So I'm gonna push that to the top, and we can use this, sure. Ideally, we'd want it to be all centered. There we go, that looks good. So this is wishbone in, but I'm not actually gonna keep the text there just because the other ones don't seem to, and I'll have to double check the spacing. We'll find out when we go to place it down. I think it's okay. Something like that, maybe. Okay, and again, so this is wishbone out is on this side, wishbone in is here, but I'm just going to delete that, and I'll keep the out on that side, and I'll move the clock into this side. Okay, let's see if we can get that lined up a little better. All right, yeah, that's good enough. So we'll see if this actually fits, and you can resize this stuff if you really want. Okay. So it asks you, it says, hey, do you want to update these symbols? And I say, yes, please do. Okay. So these two, yep, they do seem to fit. So we're just going to decide a slot to connect this to. And I think my source code, so I'm just going to use the existing code. I'm using slot 8 or something like that. So we might as well keep that the same. And what's this? Oh, and we're not going to use the VGA in this example, so I'm just going to delete that. And so we don't need the DCM or anything. Okay, that's even easier. There we go. So you can see how easy it is. Like, you just drop those slots down. And this is the... So I just connect it up like that. Again, that's because this is the out and this is the in, so that's what it's assuming. So I have this fast clock in, and we're going to use, I believe there's a clock over here. Yeah, there's 32 megahertz clock we're going to use. Let's see if that's working. Oh, so you can see, I don't know if it's working, but you can't even seem to see the wire. My experience with the Xilinx schematic editor is it's not the greatest, unfortunately. So you do get weird errors like this sometimes. You know, this is why people really prefer to use vhdl a lot of the time, but we're really just using this hierarchically. We're not trying to design, the whole project with the schematic editor. We're just saying, hey, you can just see a few blocks and click them together. All the real work is still done in vhdl, as you would expect it to be. So the other thing we're going to do is we want to connect some output ports. So I need to add a bus. I don't know if that'll work. Oh yeah, added a bus, and we'll add a IO marker. So click there, and it's an output, yes. And we just want to rename this. So how do we do that? Rename port. I'm going to call it LED out. Oops, nope. Rename net is what I want. There we go. So I rename. Is that not working? Ah, here we go. Okay, double click on it. LED out. Okay, so now we see LED out 7 down to 0. So that's looking pretty good. What else might we need to do? Well, if you're familiar with general, ISE type stuff, you'd realize that, hey, we need to point LED out to what physical pins that connects to. So this is done through your UCF file. Again, this is just like any other FPGA project. So I already have one I'm just going to copy over. And the one thing we're doing is, before we were using this, what ports were they here? Wing CH, I believe. So port CH. These were the outputs that are connected to the LEDs. So I'm going to comment them out because that Wing CH0 port doesn't exist anymore. Oops. And I'm going to add my own in. So you can see I've basically just renamed what was Wing CH0 to just be LED out 012, so part of my bus. So in theory, that should be it. So you notice, it's pulled in the somewhere this pulse width modulator block, and you can just open the vhdl source code if you want. So it really is just like a regular FPGA type project, and of course you could use Verilog too. I'm just using vhdl because that's what the rest of this project is using, but I believe normally you can combine vhdl and Verilog within a project, and I think you also can through the schematic editor as well. So don't feel that, oh, they're using schematics, it's not a real project. Again, it's just using this for hierarchy. All the real work is still done with vhdl, and you can, of course, just use vhdl. You could replace all this with a vhdl code if you wanted. So it's not, it's not a requirement that you use this schematic entry if you really want to. And what's happened here? Did I forget to give it a block? I believe I did. So I also have to copy a pwm.vhd file over. So I'm just going to copy it from when I made this project the first time. So again, you can see all the vhdl files for the various peripherals located in one spot, and there should have been a file called something like pwm.vhd. This is a file I added, so it's not part of the regular release. So there it is. So again, we'll just copy this over. So again, just like any other project. So it's good enough, and we'll put it I'll just dump it in the main directory there. So you can also, there's this nice libraries that you could, put it in with the rest of the peripherals if you want. For now, I'm just giving you a simple example. And I'm just going to point it to that file. And now we can try building this. Okay, so now sort of using the magic of TV cooking, the bitstream is done, so we'll try programming it in and see what happens. So I just go back to the ZAP, and again, the board, just confirm the board was set correctly, hit burn bootloader. So now what it should have is it should have all those LEDs connected to the pulse width modulation drivers. So if I've reloaded that blink example, it wouldn't work because the GPIO is not controlled, or the LEDs aren't controlled by the GPIO, they're controlled by that pulse width modulation block. So let's, what was that called? Blink test, okay. So I can do the same thing. I'm just gonna use, oh, so there if I hold down control, see how it says upload to memory? I don't know why that wasn't coming up before, but it was still doing it. And fire on the camera. So there's nothing, no blinking. So is that good or not? Well, yeah, I guess it's good. So let's try driving the pulse width modulation block before I sort of fire up to the final thing. So we're gonna get rid of this. There's no pin mode, and you know, actually all this, just screw it, delete it all. So what we need to do is write to the pulse width modulation block, and this is actually really easy. It's you know, super convenient, I would say. So we'll use, let's pull this back up. What we'll do is there's a few different ways you can do it. There's a macro that lets you write to it, or you can write to it as a memory mapped IO. I'm going to use the memory mapped IO in this example. You can look through some of the libraries to show you using the macro. So I have this, it's a 32-bit processor, so I have an address pointer. Again, you can see how if you're used to using C-type stuff, you can really default to that and abuse the system. So I now use this macro called register, and it's IO slot 8. So this is right from here, wishbone slot 8, and you can see how this hierarchical design makes life pretty easy. Here's the blink test, and we simply write to the to that register. So you know, let's just it's an 8-bit pulse width modulation, so you know, we can write 0 to 1, 25 to another, 52 to this one, 100, 200, 255, and I'll just do this incrementally. And we'll say, again, I'm just uploading to memory here, so it's not going to remain resident. And what you see is, so it works. So you can see that some of these LEDs are a lot brighter. So it starts off, you know, this one's basically off, dim, a little brighter, brighter still, and super bright, and then the final two are off. So this corresponds exactly to what I just did. So that's really cool. I've just made a peripheral, written to it from a soft core processor, and you can see I've just memory mapped it into the soft core processor. So, and I have a bunch of different registers. So if you're designing a peripheral, how much easier is this than trying to have some, you know, complex state machine for doing initialization and everything like that? And as a final test, let me run the complete demo. So this is just running, you know, here's this ZAP source code. And all it is a folder, and I just dumped this folder somewhere. What do I want to call it? Video. Okay. So once that's copied somewhere, we can just open it in ZAP IDE. So if I go open, and let's just point it, that INO file. So this is the complete example I have. So this is you can see how I'm just using header files to pull in stuff. Again, it very much like standard embedded development. So here I do a little more work. This LEDs, you can ignore that because they're now driven by pulse width modulators. But I use the switches, which is part of a serial I/O line, and I use the serial I/O line example. We'll drive the 7-segment display, we read a value from the ADC, and all sorts of stuff. And again, all you do is hit verify, and there's some warnings you can look through. So you can upload this. So if again, there's upload to memory, which I'll show you, that's really fast. Just like that. And if I hit upload, which is uploading it to the EEPROM, we can see this will take a little longer, so 1.7 seconds. So to view the serial port, I just open the serial monitor here. And I hit enter. So we get a bit of a menu, and for example, I can read the button status. So let me get a camera here. Maybe there's a better size. Okay, so there's the board, and here's my little serial window. So, all buttons, what are they? They're all low here. So we can see that that button choice match them. I can turn a few on. So you can see a few of them are up now. And if I do the read again, we can see that, hey, it read them successfully. And we can set a value to the 7-segment display. Let's try that. So set and ABCD. And there's an error in the vhdl that's not fixed where hex D isn't displayed right, but you can see that FE is 99. So there you go. So that's pretty cool, and that's using and this is using a hardware 7-segment driver. It's not doing multiplexing in the microcontroller chip itself. It just pushes it off to the hardware, and the hardware deals with multiplexing everything you want. And we can adjust the 7-segment brightness because it's driven by a pulse width modulator. So you can see that, oops, I used the wrong one. So you can see that you have all this control over the brightness. I think it's reverse maybe, so that's the brightest and 10 is the dimmest. So that's pretty cool. It's not just high, low, or something like that. You have this linear control over it. And the final thing it's doing is not using this at all. It's actually reading from an ADC pin, and the ADC pin is this guy here, and it uses that to update the bar graph, which is made with LEDs and pulse width modulators on each of the LEDs. So you can see that it's not just full on or full off. It's actually varying the LED intensity as we adjust as the voltage goes up and down. So it's a more linear like bar graph, not just on off completely. And of course you could do this with a standard microcontroller, but it's not quite the same. Because you may run out of pulse width modulator channels, or you'll be very busy dealing with just the pulse width modulation. This way, the microcontroller just deals with reading from this SPI ADC chip, updating the pulse width modulator settings, and then goes and does other stuff, and then says, okay, what's the new ADC setting? So it has much less overhead, and it pushes off to hardware the stuff that hardware is very good at doing quickly, the counter. That's easy to do, whereas doing a complex state machine for reading the SPI flash is better handled in software. So that's a complete example of programming a soft core microcontroller using the Papilio Pro and the ZAP ID release. So as normal, full details are in the Programmable Logic in Practice 2014 August issue of Circuit Seller. But hopefully you enjoyed the video, enjoyed the article. Thanks for watching.